So children, welcome back to Riju and PSK online classes. We are talking about physics, semiconductors, and last class we studied about, last class we actually had a recap of whatever we have been studying in the other three classes, and we discussed about how an n-type semiconductor conducts and what is the advantage of an n-type semiconductor. Now today we are going to discuss about a p-type semiconductor. P-type semiconductor. It is a semiconductor obtained by addition of a small amount of trivalent impurity. P-type trivalent, N-type was pentavalent. Example, indium, boron, aluminium, etc. There it was arsenic, etc. Now what will happen when the trivalent, what had happened when the pentavalent added? Pentavalent, the 5 electron, 4 of them made covalent bond. The fifth one was not part of the covalent bond. So that was helping us in conduction. Here there are only 3 electrons in the outermost shell, but there will be 4 silicon atoms surrounding that one. So you need 4 electrons, but there are only 3. You need 4, but there are only 3. So there is a vacancy. That is a hole. A p-type semiconductor will give an additional hole. N-type will give you an additional electron. This is the only difference. And the energy of this hole will not be in the conduction band, will not be in the valence band. Energy of that electron was also like that. It was below the conduction band, but here the whole energy will be above the valence band. So the number of electrons were greater in N-type, but here the number of holes will increase. NH will be more than Ne. Conduction is done by both electron and hole, but here electron will be less, so hole current is more. Very similar. The energy band diagram, there you know, there was the valence band, there was a conduction band, and the electron energy, that was called donor, because every arsenic was, every pentavalent impurity is donating 1 electron, but here every trivalent impurity is waiting. Give me an electron, give me an electron. It's waiting, it's ready to accept. So that is an acceptor atom. That was a donor atom. This is an acceptor atom. That was acceptor. That was donor energy level. Here it is acceptor energy level. Donor energy level was below the conduction band. Acceptor energy level is just above the valence band. Almost the same energy difference. When the trivalent indium impurity is added to a pure silicon crystal, 3 valence electron of indium form covalent bond with the electrons of neighboring 3 silicon atoms. There is no electron for the 4th silicon atom. This creates a hole. That is it. This is the theory. Okay. Now the diagram. You remember the previous one, almost similar to that one. Here, okay, I will do my own. This is the NCERT version. Okay. Now the idea was this, the indium atom with the effective +3 core for the outer shell. I told you why it is +3. That want to make a covalent bond with the neighboring 4 silicon atoms. So there is one silicon, there is one silicon, there is one silicon, and there is this 4th silicon. Okay. Now silicon, each silicon will give 1 electron for the covalent bond. Now indium will give 1 electron here, 1 electron here, 1 electron here. Bapre, where is electron for the 4th covalent bond? There will be no electron for the 4th covalent bond. So this will be a hole. This is a hole. So every trivalent impurity will give you 1 hole. Right. Now if you look from the eye of this hole, okay, then this dopant impurity atom will look like this. It look like this one. There is a hole with a positive charge, okay, and there is a core with an effective negative charge. Core with a negative charge, hole with a positive charge. Okay. You can't remove hole, but you can add an electron. You can add an electron. Okay. Now this is balanced. But if you add an electron, what will happen? this will become a negative ion, because the whole system is neutral. You give an electron to this one, then that gets an additional negative charge. Okay, so when you give this one, this hole, an electron, so you can say electron will combine and remove this positive charge, so what is remaining is only the negative charge of the core. Clear? So when you add an electron to this impurity atom, effectively it will become a negatively charged ion. You are giving, no, think like this, this is a neutral atom, you are giving an electron, so that becomes negatively charged, right? So that is what marked here. Every impurity atom here has a hole. So if you put an electron to this one, this system is getting a negative charge. It becomes a negatively charged ion. That is given in the NCERT textbook like this one. Just go through the diagram, study that one. Acceptor core. This is acceptor core. Okay. Now, acceptor atoms. This is not pentavalent, I am sorry, that is not pentavalent, it should be trivalent, typing error, it is copy paste, right? So that is why this is not pentavalent, it is a trivalent. The trivalent impurity atom that donates one free hole, one free hole to the semiconductor is called acceptor atom. One acceptor atom gives one hole, that is correct. Acceptor level. The energy level corresponding to the hole in the acceptor atom is in the forbidden energy gap. It is slightly above the valence band. This level is known as the acceptor level. Definitions are very similar. I was actually copying pasting, that's why this errors. Be careful about that one. Diagram wise, your conduction band, valence band, and see this dotted line represents the acceptor energy level. It's 0.01 to 0.05 electron volt, very small difference. So at any time you can have hole in the valence band. This hole will easily, that hole will easily create holes in the valence band. Okay, you can see here there is one electron, and see I told you in CRT diagram this is inverted picture of that one. Okay, so these dots represents electron. This is electron, and these are holes. Fine. Now this one is again an electron. Out of this many electron, okay, you have one electron there. You can have an electron in the conduction band only when you have a hole in the valence band. So one of this hole and this electron is a pair. This is a pair produced due to thermal agitation, thermal energy. What about other holes here? There are 1, 2, 3, 4, 5, 6, 7 holes are there. And how are these holes produced? These are produced by the impurity holes. So there are two types of holes here. One is electron hole pair created by the thermal agitation, other is by the impurity. That means you have added 7 trivalent impurity. 7 trivalent impurity, that's why you have 7 electrons. So if you add 100 trivalent impurity, what will happen? You will have 100 holes here. So you can increase the number of holes by increasing the amount of impurity added. Okay. Now, what about conduction? I mean, these points to be noted. Just like N-type semiconductor was not negatively charged, P-type is also not positively charged. But when a nearby valence electron fills the hole, the indium atom becomes negatively charged immobile ion. Number of holes will be much greater than the number of electron, but Ni square is still equal to Ne into Nh, because when the number of holes will increase, the rate of recombination will increase, so that will effectively decrease the number of electrons. So number of electrons will decrease, number of holes will increase, the product will remain the same always. Fine. Now the conduction, I think I can explain that's in the same way. Conduction, if you have a p-type semiconductor, what is a p-type semiconductor? There will be large number of holes because of the, depending on the doping impurity, doping concentration, but there will be few number of electrons. So when you connect this to a battery, you give an external electric field, then there will be electron moving in this direction, producing electron current to the right side. Due to the movement of shifting of electron in this side, these holes will also move to the right side, that will produce Hall current. And we can see that IE plus IH will be equal to the total current, but the Hall current will be much greater than the electron current. That's the point. Under the applied electric field, there will be large Hall current and the small electron current. That's it. So, very similar. I said this can be studied once you study that one. Now, for your board point, I have a comparison chart. Study this intrinsic semiconductor, extrinsic semiconductor comparison. These are pure semiconducting tetravalent crystals, but these are semiconducting tetravalent crystals doped with impurity atoms from group 3 or 4, group 3 or 5. Their electrical conductivity is low. Their electrical conductivity is high because you have more number of electron and more number of holes. There is no permitted energy state between valence and conduction band. It's forbidden. But here there is permitted energy level. One is known as acceptor level, another is known as donor level. Number of free electrons in the conduction band is equal to the number of holes in the valence band. That's why we always write here Ne is equal to Nh, which is equal to Ni. But here we know in N type Ne is greater, in P type Nh is greater. Their electrical conductivity depends on temperature. But here their electrical conductivity depends on temperature to some extent as well as on doping concentration, more on doping concentration. This comparison should be understood. There is one more, the comparison of P type and N type. N type semiconductors. These are extrinsic semiconductors, okay, obtained by doping pentavalent impurity atoms of group 5 to germanium or silicon. You can give an example, arsenic. But here it is from the third group, indium is an example. Impurity atoms added provide free electrons and are called donors. You get more electrons, but you get more holes, okay. Vacancies of electrons or holes and are called acceptors. The donor impurity level lies just below the conduction band. The acceptor impurity level lies just above the valence band. The electrons are majority charge carriers, holes are minority charge carriers. See, hereafter I will be using these sentences and these usages more and more. Electrons are majority charge carriers, holes are minority charge carriers. What about P type? Electrons are minority charge carriers and holes are majority charge carriers. The free electron density is much greater. Ne is greater than Nh. Nh is very greater than Ne. But don't worry, in both cases, Ne into Nh will be equal to Ni square. This is one area where we can expect a numerical question. Okay. So, this is all what we have the basics of semiconductors. Now, we are going to apply this in making devices. Okay. Now, one example, let's do this from the NCERT textbook. Pure silicon at 500 Kelvin. Pure silicon means what is it? It's an intrinsic semiconductor. Pure silicon, intrinsic, has equal number of electron and hole concentration 1.5 into 10. So, I can write Ne equal to Nh, and that is also known as the intrinsic carrier concentration, and that is given as 1.5 into 10 to the power 16 per meter cube. In 1 meter cube, this many free electrons. Doping by indium increases. Okay, this is before doping. Before doping. So, what about after doping? After doping. After doping, what happened is that the NH, it's indium. After doping with indium. Indium means what material is that? Indium means it is trivalent. So, this is a P type semiconductor. NH increases. The new value of NH is 4.5 into 10 to the power 22. See, it was 1.5 into 10 raised to 16. It increased to 4.5 into 10 raised to 22 because we added impurity. Okay. What will happen to Ne? What will happen to Ne? That's a question. Will it remain the same? Answer, it will not remain the same. It will not increase or remain same. It will decrease. Why does it decrease? It's because when you have this many number of holes compared to the previous value, see earlier there were electron hole recombination, but that was less. But now the number density of holes increases. More holes are available, so the combination will also increase. When combination increases, you will lose electron. And that is why electron number will decrease. Find the concentration of electrons. How to find out the concentration of electron? Understand that you use the equation NeNH equal to Ni square. So if you want the new value of Ne, simply take Ni square divided by NH. What was Ni? It was 1.5 into 10 to the power 16. You square this, then divided by the number density of hole, the new density. This is the new density, okay? New density is given as how much? 4.5 into 10 to the power 22. This is your answer. Okay, so this question gives you this idea why the concentration of electron decreases. It decreases because of increased electron hole recombination. If you want a better thing, Ne equal to, I think, 1 minute. Yeah, that is it. You wanted Ne into NH equal to Ni square. So that you just work out that one, you get the answer. Okay. Alright, so from there, next question. In an N-type silicon, which of the following statement is true? N-type silicon means it's a negatively, you have extra electrons in that one. Okay, electrons are majority carriers and trivalent atoms are added. No. If you want N-type, you want pentavalent impurity. One electron number is more. So what is the option? Electrons are minority carriers, not correct. Holes are minority carriers, that is correct. Holes are minority carriers and pentavalent atoms are the dopants. So this option is correct. Option C is correct. In a p-type silicon, p-type means you use trivalent impurity and the number of holes will be more, electron will be less. What is the correct option? Holes, p-type, electrons are minority and pentavalent, holes are majority. Holes are majority carriers and trivalent atoms are the dopants. That is the correct option. Option D is correct. Okay. Now, carbon, silicon and germanium have 4 valence electrons each. That's correct. They belong to the same group. These are characterized by valence and conduction band separated by energy and energy band gap. And the energy gap is given Eg of carbon, silicon and germanium are given. Which of the following statement is true? Why carbon is not a semiconductor? I think we discussed in the previous class, the energy gap of carbon is greater than that of silicon and that is greater than that of germanium. Option C is your right answer. Okay. Now, from here onwards, we are moving to a new topic, application of all these ideas that we studied so far. So, dear children, so far what we studied is about two types of extrinsic semiconductor. One is p-type, another is n-type. P-type is formed by doping trivalent impurity where holes are more, and n-type is by doping with pentavalent impurity where electrons are more. So, generally I can represent this material as larger number of holes, okay, larger number of holes. Understand that there are a very few number of electrons inside this, and here what I can do is this, I can represent it as a larger number of electrons and few number of holes. Now, if you join them, like these are actually metals like silicon and germanium, these are metalloids, you studied that, you can fuse them, melt them and join them, make a single block. We can make them into a single block. So, you will get something like this with a junction. One side is P, other side is N, this is a junction. Alright. so many phenomena will take place here, and this is a beautiful device. This can be used in making so many other electronic devices. This is what we call as a PN junction. It's what we call as a PN junction. How is a PN junction made, and what are the different processes across the junction as well as in the material is what we are going to study right now. So imagine holes more, electrons less. There is a concentration difference. If you think about electrons here, concentration of electron is less here, more there. Similarly, concentration of hole is more on the p side and that is less on the n side. You also should remember one more point, that this thing, one more point, that if you have a p-type material, I told you a p-type material has got a hole. It has got a hole and a core. Similarly, an n-type material has an electron and a core. This is neutral, this is also neutral. P-type is not a negatively charged, p-type is not positively charged, n-type is not a negatively charged, both are neutral. Now there is a fifth electron here and there is a vacancy of electron. I told you earlier that if this system loses this electron, if this electron is lost, then this will have a positive ion. And if that electron comes here and that will occupy this hole, and you will get an extra electron here. This is an immobile. This is immobile positive ion, this is immobile negative ion. This is one possibility. So when you make a junction like this one, this is possible. This can lose an electron and this can gain an electron. There you will have a positive ion, you will have a negative ion here. Positive ion in the n side, negative ion in the p side. This mechanism should be clearly understood. Okay? Once more, a p-type material and an n-type material. During our discussion I told you, and in NCERT also this is written clearly, that p has got a hole, but this total is neutral. N has got an electron, but that is also neutral. Okay. You should know that we are not giving electron, we are giving a whole arsenic atom. That's why that's a neutral arsenic atom. This is actually arsenic atom. I can give an example. This is the indium atom. This is a neutral atom. This is again a neutral atom. There is a vacancy of electron not for the covalent bond, but in the valence band it has got 3 electrons. But what will happen if this arsenic atom loses this 5th electron? You are removing 1 electron from the outermost shell of arsenic atom. There are 5 electrons, you are taking the 5th electron. What will happen? Arsenic atom will become a positive ion. Indium has got a neutral, indium has got 3 electrons in the outermost shell. What will happen if you put 1 more electron in the indium atom? If you put 1 more electron in the indium atom, then the indium atom will become a negatively charged ion. Arsenic on the n side will become positively charged, indium on the p side will become negatively charged if this happens, if electron transfers like this. And if there is a positive charge and a negative charge, there can be an electric field. There can be an electric field between them, and the electric field will be from n side to p side. This is the mechanism that I am going to explain. Okay, watch. This is called PN junction. PN junction. The manufacturing or the industrial production of a junction is very complicated. Lot of techniques, lot of mechanisms are there. But what is given in NCERT is a very simple idea. What is it given? A selected part of P silicon wafer. You have a silicon wafer like this one. This is a silicon wafer which is P-type. P-type silicon wafer. Okay. A selected part. This is a selected part. Is converted into n-type. It is already p-type, but it is converted into n-type. How to convert a p-type into n-type? In p-type holes are more, n-type electrons are more. See, if you put a more pentavalent impurity into the p-type, then that can become an n-type. Manasilayo. You are putting more pentavalent impurity in this region. So that will become an n-type semiconductor, the other one will become a p-type semiconductor. This is done like it's an industrial process. then you will see this line, this separation, this one. What is that? That will have n-type material on one side and p-type on the other side. That become a p-n junction. The wafer now contains p region and n region and the metallurgical junction between n and p. That junction is what we call as a p-n junction. P region has high concentration of holes and n region contains a larger number of electrons. How a p-n junction is formed? If question comes, this is what you have to write. What is the method? You take a what material? You take a p-type material. Then select some portion, any portion, select some portion and you add a pentavalent impurity so that this become an n-type semiconductor. Okay, so there is a junction formed here. This junction throughout has n on one side, p on the other side, n here, p here, so this become a p-n junction. N has got more electrons, electrons are majority carriers, p has got holes, holes are majority carriers. N has got a minority carrier hole and p has got minority electrons. This is how a p-n junction is formed. What is a p-n junction? How it is made? With the diagram you can answer it. Each slide is an answer to a question. The diagram I did, p-type semiconductor, n-type semiconductor. You can see this thing. Negative acceptor atoms. The large circles are negative acceptor ions. Negative acceptor ions, p side, indium. Here, positive donor ions. Positive donor ions. Okay. Now you should know that this is a neutral atom. This is a neutral atom. This is a neutral atom. This is again a neutral atom. But it has got a fifth electron, this has got a hole. Okay. You are going to combine them. So I said if this electron can come to this hole, electron will disappear, this will become positive ion, hole will disappear, this will become a negative ion, positive charge here, negative charge here, and an electric field can be produced from n side to p side. This mechanism should be clearly understood. Now when you join like this, you get a picture like this. What happens? Two important processes occur during the formation of p-n junction. This was a CBSE board question. What are the two important processes across the p-n junction? Answer: diffusion and drift. Diffusion and drift. Okay. And the NCERT diagram is there, but I will do my own way. Okay. What happens here is that you have this p-n junction. See, this is the p-type material, this is the n-type material. Which are the majority carriers on the p side, which are the majority carriers on the n side? On the p side, you have larger number of holes. On the n side, you have few number of holes. What will happen? Diffusion will take place. Diffusion is a process of distribution due to concentration difference. High concentration, low concentration. So the holes will go like this. This is called hole diffusion. Think about the electrons. Large number of electrons here. Very large number of electrons. Very few number of electrons. Concentration of electron is more on n side, less on the p side. So electron will drift. Electron will diffuse. Electron will diffuse to this side. Electron diffusion is from n side to p side, hole diffusion is from p side to n side. What is diffusion? The process of movement of holes from p side to n side and electron from n side to p side due to what? Due to difference in concentration is called diffusion. Out of the two important processes, one is diffusion. Okay. When they diffuse, I told you when they diffuse, electron on the n side will go to p side. Electron from n side will go to p side. So here you will get positive ions. And here you get a negative ions. This will create an electric field. This will create an electric field across the junction from n side to p side. There is an electric field. there is an electric field. If there is an electric field, what will happen to the electrons in the system? What will happen to the electrons in the system? That is what you have to answer. With the answer to this question, see you in the next class.